Hello students, welcome back. In this video, I am going to solve some questions from carboxylic acids and their derivatives like esters, acid chlorides, and hydrides, amides, etc. The first reaction is about ethanoic acid. When it is treated with the thionyl chloride, then what should be the product? This is a simple nucleophilic substitution reaction and it is going to form the acid chloride. So in this case, it is ethanoyl chloride. This is one of the derivatives of carboxylic acid as it is prepared from the carboxylic acid. Now, this acid chloride is treated with 3-methyl aniline. So what is the structure of 3-methyl aniline? So you have to write that in detail so that you can predict the next product. So from here, 1, 2, 3. At third position, there is a methyl and this is aniline. Now, what sort of reaction should happen? There is a nucleophilic substitution on this nitrogen and the chlorine will leave the molecule. Therefore, you are doing acetylation on the nitrogen. What will be the byproduct? H from here, Cl from here. HCl is a byproduct. What is the main product? That is N-acetylated aniline, like this. The methyl will remain as it is. Many students get confused here in this step because they think that the acetylation happens on the benzene ring. That is not correct because nitrogen is electron rich as compared to the benzene because the lone pair of electrons present on the nitrogen which is free to attack here. Whereas in case of the benzene, the pi electrons has to attack and they lose aromaticity in this process. That's the reason the acetylation is happening on the nitrogen. Now, once you get this, what you have to do? Treat it with lithium aluminium hydride. Lithium aluminium hydride is a strong reducing agent. It reduces the amides also. So when it reduces, first we get an alcohol here, which upon dehydration, it will form imine. Imine upon reduction, we are going to get a completely reduced N-alkyl product. So what I mean is you just have to write down the hydrogens on this particular carbon. So it's going to be CH2, CH3 as it is completely reduced. What about this? This will remain as it is. So let me repeat this. First, the CO group will reduce to alcohol, which will undergo dehydration to form imine. Imine upon complete reduction, you are going to get the N-alkyl amine. So this will be the final product. And just check where it is. It is in the option D. So you can see they are meta to each other and then there is a N-ethyl aniline. Hence the final answer is option D. For this question, you have to identify the final product for the sequence of reactions for the given lactone. Lactones are cyclic esters and esters are the derivatives of carboxylic acid. So this 5-membered lactone is treated with the double Grignard reagent. You can see that there are 2 MgBr attached to the 2 carbons. So that's why we can call this as double Grignard reagent. So how many carbons are there? 1, 2, 3, 4. You write down 4 carbons like this. Don't make any mistake here because of the long chain molecule. Now, what is the first step? The first step is attack of this Grignard reagent. So you can polarize the molecule so that it will be easy for you to identify the mechanism. You can see it will open up the ring now. So the CO is attached to this carbon. So CH2. And how many CH2 we have here? 1, 2, 3. So 1, 2, 3, which in turn is attached to the MgBr like this. Still, there is one Grignard reagent here. What happens to this group? You can see here there are 3 CH2. So 1, 2, 3. And then this will be attached to OMgBr like this. Many students, what they think that because there is a OMgBr, this is also Grignard reagent. No, this cannot be organometallic compound because the metallic part is not attached to the carbon, but it is attached to the oxygen. So this is a salt, right? It's a counter ion. MgBr is just a counter ion to balance this O minus. What should happen in the next step? Still, we have a reactive ketone here and then there is 1 mole of Grignard reagent. So ketones do react with the Grignard reagent. It will undergo addition reaction and it is intramolecular. So how many membered ring are we going to get? Count from here, 1, 2, 3, 4, 5. So you write down that first. It will be very easy to find out what will be the final product if you write a 5-membered ring. So take any carbon. So I'm going to take this carbon wherein this is becoming O minus. Why O minus? When this attacks here, oxygen has to take away these pi electrons. It will be balanced by the MgBr counter ion. Now, look at this carbon. It is still attached to this alkyl part. So 1, 2, 3. You write down 3 carbons. 1, 2, 3. Which is in turn attached to OMgBr. What should happen in the next step? There is a hydrolysis. So hydrolysis means what? You are trying to replace this MgBr by proton. So you are going to get the corresponding alcohol. So we can write this in this step itself, right? Then what happens? In the final step, you are adding PCC. PCC is an oxidizing agent. It will convert primary alcohol to aldehyde, secondary alcohol to ketone. Tertiary alcohol will not undergo reaction. Look at this. This is a tertiary alcohol. So no reaction with PCC. What about this? This is a primary alcohol. Hence you are going to get a aldehyde over here. This will remain as it is and you can count here CH2, 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 3 carbon and at the third carbon there is an aldehyde like this. This is our final product. So it cannot be this, this or this. So which is the correct answer? It is as shown in option D. The next question is based on the decarboxylation of the given carboxylic acids. You have to arrange them correctly in the order of their decarboxylation. First of all, what is decarboxylation refers to? Whenever we remove carbon dioxide using strong base like soda lime under heating condition, we call this as decarboxylation. Generally, this is not recommended because the living group here, what we have is a carbanion. So these are not stable, that's the reason. But if there is any stability factor which will stabilize this carbanion, then the decarboxylation process is enhanced. For example, in third molecule, you can see that this is a beta keto acid. In acids like this, when the carbanion is formed upon decarboxylation, you can see that it will be stabilized by resonance like this. Because of this, the decarboxylation is highly recommended for beta keto carboxylic acids. Similarly, let's check for the second molecule. The second molecule is also having some additional factor which can stabilize this carbanion. What is it? There is a double bond. When this can undergo decarboxylation, you can see that it is forming allylic carbanion. Allylic carbanion can undergo resonance. That means what? The corresponding carboxylic acid can undergo decarboxylation. Then how do you decide between these two molecules? Because both of them are stabilized by resonance after decarboxylation. See here, oxygen is the one which is stabilizing that negative charge. Oxygen is an electronegative element. It can withstand this negative charge. That means it is stabilizing this better as compared to the allylic carbanion. Hence, the keto acid will undergo decarboxylation better as compared to the allylic carboxylic acid. So 3 must be greater than 2. What about 1? In case of 1, when it undergo decarboxylation, the negative charge will be on the vinylic carbon. When we have negative charge on the vinylic carbon, then it cannot be stabilized by resonance. That means what? Here it is least stable. So 3 greater than 2 greater than 1. And what is that option? Option A. Therefore, the final answer is A. For the next question, you have to find out what is the final product when the given ester is treated with the deuterated lithium aluminium hydride. Here, instead of hydrogen, we are using deuterium. That means what? It is isotopically labeled. So why do we use these isotopically labeled compounds? Because to know the mechanism of the reaction. That means what? The reduction of the ester from the lithium aluminum hydride, which is a strong reducing agent. What should be the product? You can predict only when you know the mechanism of the reaction. See here, the mechanism will remain same whether you use hydrogen or deuterium. It's just that when we use heavier isotope, the reaction will get slower. That is the only difference. Otherwise, the product formation, the mechanism, everything will be same. The reactant here is methyl benzoate. What should be the first step? The deuterium ion should attack this carboxyl carbon and the methoxide will leave and we are going to get an aldehyde, and it is labeled because the deuterium is present in the aldehyde functional group. Will the reaction stop here? Are you going to get option A as an answer? No, because aldehydes are further reacting with the deuterium ion what we have, because there are 4 moles, right? So that means what? This deuterium further attacks this carbonyl carbon and it will undergo further reduction, and you see that this carbon is attached to 2 deuterium and this will become O minus. The O minus will be stabilized by the counter ion lithium ion. Now, what is done in the last step? Hydrolysis. That means what? We are getting rid of this lithium ion and replacing thereby the proton. So, it will become OH. So, this is nothing but alcohol. And here, what do we have? Deuterium. So, when ester is reduced using lithium aluminum hydride, the final product is an alcohol. But where is the deuterium? Directly attached to the carbon but not on the oxygen. Therefore, what should be the final answer? As shown in option D. Therefore, the correct option is D. The last question is from the acidic strength of carboxylic acids. This is again one of the most frequently asked concept from the carboxylic acids topic. There are 5 different carboxylic acids given here. You have to arrange them in the decreasing order of their acidic character. Whenever you see a benzoic acid, always remember about the ortho effect. What is ortho effect? If there is any group at the ortho position, whether it is electron donating or electron withdrawing, doesn't matter. If there is a group at the ortho position, it always increases the acidic strength of the corresponding carboxylic acid. Why is it so? This is due to steric hindrance. The group present at the ortho position need space. Same with the COOH group. Then what happens? There is a competition for the space. Then the bond which is weak here. Which bond is weak here? You can see that the oxygen hydrogen bond is weak. This is ready to cleave because when this hydrogen goes as a proton, it will be, the negative charge will be stabilized by the resonance. So what happens? This bond is considered as weak. So when there are 2 groups at the ortho position, it will further weaken this bond and kick out this hydrogen as a proton, and anything which donates proton is an acid. More the groups at the ortho position, more is the acidic strength. Hence, the compound 5th is the most acidic among the given molecules. But there are such 2 options. So identify the molecule which is next acidic. As I told earlier, look for the group at the ortho position. So we have OH and methoxy. But look at the options. By the options given, it's obvious that this orthohydroxybenzoic acid is more acidic in nature. This is due to intramolecular hydrogen bonding. You know that the carboxylate will be stabilized by the hydrogen. Hence, this will be more acidic as compared to the methoxy. So, we will have 2 followed by the 4. So, both of them have the same. Now, how do you decide between 1 and 3? See, hydroxy is a electron donating group through plus R. So, anything which donates electron will decrease the acidic strength of the molecule. So, 3 is supposed to be the least. And what happens to the normal benzoic acid? That is more acidic than the parahydroxy benzoic acid. Therefore, which will be the correct option? Option D. I hope this video helped you, and if it is so, please do like, share and subscribe the channel. In the next video, I'll come up with the questions from the amines topic. Thank you.